when I left, exactly.
I am the new Eitan.
Okay, so Eitan,
Okay.
I'm at the that exercise 5.2.1.
Excellent, excellent. So last time we talked about control and how we want to control the system that is non-deterministic using statistics, and we said we will need non-parametric statistics because we don't understand the distribution. And the key concept we introduced last time was the distribution function, which is a function of, that is equivalent to the probability measure, and it represents the probability that the random variable will be less than a certain value. So if you think of chatbot and you think about you're interested in what's the average number of people that end up with a human agent, then basically the distribution function will give you things like what's the probability that the number of calls that ended up with a human agent is less than 20%, something like that. Okay, so now we're taking the next step and we're trying to basically create from sampling the distribution function. So based on the sampling, we get some points from the sample space. So if you think of the dice again, you take the dice and you roll it 100 times. So n here is 100, x1 to xn, and you get a series of results of the dice. 5, 2, 3, 1, 1, 1, 1, 2, 3, and so on. So you're just getting results. And now, an intuitive way of estimating what the probability is that a result is less than 3 is to take all the results that were less than 3 or equal and divide it by the number of rolls of the dice. So if you roll the dice 100 times, you would look at the number of times that the dice was less than or equal to 3, and you divide it by 100 to say it was 20. So 20 over 100, it's so the probability is 0.2. So that's the idea of of a central concept that we're going to be using, called the empirical distribution. Okay. Now, for instance, as an example, say we are interested in the probability of the dice giving a number that is less than 3. So there's 3 options, right? Three cases in which the dice will give a number that is less than 3. It's 1, 2, and 3. So the probability that the dice will be the theoretical probability. Here it's easy. Everything is simple and you understand the distribution. So what's the probability that the dice will be less than or equal than 3? Question mark?
Half?
Yes, exactly. Because there's 3, everything is, if we don't have any other information, so everything is equal. Each result is 1 over 6. And we have 3 results that are less than or equal to 3. So it's 3 over 6, so it's a half. Okay? So that's the distribution function at the point 3, which means the probability that you get a value that is less than or equal than 3. It's a half. Now, if you start throwing the dice, rolling the dice, you would not see a half necessarily. You would see something that is more or less a half. So if you get the results, like if you get, say, 1, 1, 2, 1, 2, 1, 2, 2, 2, 6. So what's the empirical distribution? I'll be more specific. Say we've rolled the dice and we got the unlikely result of 9 times it was 1 and 1 time it was 6. So what's the empirical distribution? No, the theoretical distribution is a half. Now, what's the empirical distribution that we're going to get? What's the empirical distribution of an even getting an even number when you look at rolling a dice that gave you 9 times 1 and 1 time 6? What's the empirical distribution going to be?
This is for the even number? So that would be 1 over 10.
No, not the even number. Sorry.
Oh,
less
that's what
than
you
3.
said.
Sorry.
Less than 3.
Debbie.
You said even number.
Yeah. I confused. My confusion. Less than 3. So you have 1, 1, 1, 1, 9 times, and then 6.
So it'd be 9 out of 10.
Yes. So you see, the empirical distribution doesn't need to match the theoretical distribution. So how do we connect between the two? So that's one of the exercises Guy did. So maybe Guy, if you like, if you're willing, you can show the exercise that you did there on how the empirical distribution converges to the theoretical distribution when you
Sure, just give me a few minutes to find it.
you just okay, sure. I think if
Eitan, so you're basically saying if you do it enough times, the empirical should converge to the theoretical. So even though the empirical with the example you just gave us was 9 out of 10, if you do it enough times, it should converge to whatever, a half that we said, right?
Yes, exactly. And some people think about this as the definition of probability, but that's another story. It will take us hours to discuss. And also, if it doesn't, and you have some expectation, it will tell you something about the fact that you don't understand the reality you're observing. And that's the basic of statistics. So statistics has to do with setting up an expectation of what we believe the reality is, which in our case is a half, and then seeing what happens. And if it's too far away from our expectation, we say, well, maybe it's not correct that it's a half. And we do that in a rational way, and we can say what's the probability that we make a mistake and things like that. So that's statistical tests, okay? So conceptually, this is a very central theme to what we are trying to do here, being able to set up expectation about reality in terms of probabilities and then checking them. Okay?
Can you open the notebook link I just sent in the chat?
So Sam can open it for you. Just tell him where to press, because there's a link. Okay. If
It's
Sam
in the chat.
has
You're sharing screen. It's Sam. Sorry, Sam. If you can just open it.
So Eitan, so is this why in machine learning they want such a large training set? Because
Yes.
the larger the base
Essentially,
is,
yes.
the better you can get to the theoretical probability?
Yes.
Okay.
There's more to say about it. We're touching on the conceptually, we're touching on the issue of what is called concentration of probabilities.
What?
Concentration of the probability mass. Okay. So
If you slide down a bit,
Mhm.
What do we do though if it never what if the theoretical never matches the reality because there's a hidden entity affecting the data?
Excellent. That's exactly testing. We're testing the system. So if the system
Sam,
doesn't
can you
behave,
go just a bit more to the plot below? You can see it's kind of converge, but you can see it's never really does converge. You can see in this case, the example, the x-axis is the size of the data set. You can see it's very noisy at the start, but it doesn't really flat out. Not at least for 1,000, a data set of size 1,000. It's also always remained kind of noisy, but it's white noise around the half.
So I guess hypothetically, let's say you had a magnitude multiplier in there that added fuzz or chaos, but you were still able to converge within your bounds. Do you care if you're getting your machine learning to be a 90% match, if that satisfies your requirement? Because that would...
you don't care.
But
let's think about the chatbot example, for instance. So what do I want? Why do I want you to tell me what's the percentage of calls that will go to a human agent? The reason I want you to tell me that is because I'm going to have a team of 3 people that will answer calls. And now I need to know if there should be 3 people or 6. But if it's 3 people and the 3 people will be able to handle, the 20% and the 23%. Doesn't matter. They'll still be able to handle it. If it will be 23%, they'll be a bit overwhelmed maybe. If it will be 18%, they'll go and drink some Coke. Okay. So as long as it's within my control limits, they're going to be happy. But if it will go from 20% to 40%, I had to have 4 people maybe or 5 answering the phone. Then I'm in trouble. So what I'm really concerned is when it goes out of the control limits, not when it fluctuates around the control limit, you see. Does that make sense?
The only source of noise here is just the random chance. There's no like external noise. So because you assume when you're rolling a dice that you're replicating the process exactly. There's no like measurement error or anything like that. So you should, if doing it, assuming every die is done exactly like perfectly.
yeah, they're not weighted.
Whatever. Yeah.
That's exactly the thing that the book talks about in details in the first chapter. So we need to think about the factors. We need to go through the scientific process of defining the right experiment. If you don't have the right factors, if the factors don't appear in the data at all, and you're not aware of the fact that the weather influences your model. So the model will work now, and in 3 months the weather changed. It doesn't work. So all your predictions are nullified. So you just missed a big factor that is influencing the problem, and you didn't understand that it influences the problem. Then you can't analyze it. It's impossible to analyze something if you don't understand the factors that are impacting it. At least this is the scientific process, which I allude to in the first chapter, basically. So this lies at the basis of the approach here. Okay, you have to define the right You have to go through the scientific process. You have to define the right experiments. You have to define the right independent variables. And then you get to the point where you start analyzing things and using statistics. Okay? So that's a very good, important discussion. This is at the core of the ideas here. So, Guy, can you explain what the distribution function is that you estimated using the empirical distribution?
You can see it on top. If you go, Sam can go just up a little bit to the functions. I start same as the exercise by defining just a bit more. Great. A dice, which is just like the regular dice, 1 till 6. These are the options, and n is the number of thrown being made. Is even is a function that rolls the dice n times and returns is it even at the end. The 1 if it's even, 0 if not, and is odd is the complementary one. And we try to estimate f of 0. You can see it below, which is just as Eitan defined it, which means what is the probability of getting 0 in the which type of is? The odd one. To get f of 0 is just getting an odd, and f1 is actually getting both of them. This is the same as Eitan described it. And below you can see as I increase the n, the number of dice toss, you can see the estimation of the probability of getting an odd number. And below it, you can see the same for getting an either even or odd, minus the getting odd, which accidentally looks exactly the same if you go just a bit lower. Start with a bit more noise because it has 2 random variables, but it does converge to the same value. It just starts much noisier.
They should look very similar because their probabilities are the same.
Yeah, they're representations of the same thing, so yeah, they should be the same.
Well, that's just random chance that this didn't happen. If you did it again, it would be like this is just one. Wait,
yes, actually, there is no reason. You're right. There is no reason for the noise to be bigger for one of them, but less for the other.
Yeah.
Just random chance. We'll see that the start is also always very noisy, but the direction is random.
Yeah, actually, what you're plotting here is this is just 1,000 dice throws, right? So what happened here is just a function of what happened in the first.
No, let's say it doesn't really 0. Let's look at 200. 200 means it's the average after 200 dice rolls. 1,000 on the x-axis is the average on 1,000 x. So you see.
That's exactly what I mean. So like early on, it's just the average of the few dice rolls. It's not. This is just one experiment.
Yes.
Yeah. It just means that as you roll more dice, you get closer to half.
Exactly. Yes.
You get close to the theoretical distribution, basically. That's and the random variable, just Debbie, for your clarity here, the random variable here is not the random variable we started with. It's the random variable of even or odd. Okay.
Okay.
So I hope this clarifies things a bit. And is interesting. I hope it's interesting. I'm going to add some solutions. There is a solution now for 5.2.1, and then I'll add solutions also to the next few exercises, and we'll continue next week. And thank you for your patience today. with the technical difficulties. So I think, Andrew, it's time for you to stop the recording.
Yes, sir.